So it was very easy to find eigenvalues of the translation operator on a circle of L sides or n sides, finite number of sides. What are the eigenvectors? We in principle know them because we have projection operators in slightly awkward form, but actually the problem is so simple we can just write them down, so let's just do it. The eigenvalue equation is, I have a matrix phi. There is an eigenvector which we'll label k because we have k different eigenvalues. And we want to find a matrix such that if you multiply that matrix by translation operator, you just get the eigenvalue back, and eigenvalue was the primitive root to kth power. This is so simple, we can do it by hand. Here is the translation operator or the shift operator. One lattice shift and zeros every place else. Look at candidate for eigenvector entry 1 omega to the k omega to the 2k dot 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 omega to the n, if this is n-dimensional vector, to the k. So now what happens is when you multiply by shift operator, this guy becomes the first, this guy becomes the second, and then cyclically, one ends at the end. So what it means is that every entry has just been multiplied by omega to the k. So this is actually an kth eigenvector obtained by guessing, but it doesn't matter, whatever works. Now, usually eigenvectors can be normalized any way you want, but it's very natural to require that they be unit eigenvectors. There are n components here, and if I put 1 over square root of n and absorb that into definition of the eigenvector, then the following thing will happen. This will be normalized correctly, and then I dot this product. I get, for every entry, I get 1 times transpose omega k times omega minus k, that's 1. So I get entry 1 every place from 0th to n minus first element. And I pick up square root of n twice, so I get 1 over n. There are n entries divided by n, that's 1. So this indeed is an eigenvector and a unit eigenvector. These eigenvectors are orthonormal, so they're unit eigenvectors, but so let's take two different eigenvectors. Now, when I look at this product, then I get just two complex phases multiplying entry by entry. And remember what these guys look like. K and then raised to integer powers, 0, 1, 2, to n minus 1 power. So, and if one is transpose, there'll be minus omegas. So by our definition of omega being a negative root, doesn't matter, you get e to the I 2 pi over n, that's just omega itself. It's raised to power k or it's raised to power j, but with relative sign, because one is complex conjugate. And then as you go 0 first component, you get this factor here. Now what is this? It's very easy to understand what this does in a Gauss complex plane. These are roots of unity, so there is a unit circle. And the first eigenvalue lambda 0 is a real number 1. The second eigenvalue, multiplied by something, doesn't matter, is this. And what this sum does is it goes through all possible eigenvalues and adds them up. And what you realize immediately, that these eigenvectors, if there is an even number of them, it's obvious that they always appear in pair and they cancel. And if there is an odd number of them, they also cancel because they're distributed like equal weight things. A equilateral triangle is the center of the circle and stuff like that. So we find out that if k is not equal to j, this averages to 0. And we already have shown if k equals j, this is 1. In other words, this is the one possible definition of Kronecker delta function. If k and j are the same, then we get 1. If they're different, we get 0. But notice this is intrinsic to periodic problems. This is really a circular Kronecker delta. In particular, what it means is because we are looking at a phase, anytime we exceed the n sides, I'll just get modulo 1. So this Kronecker delta actually also makes sure that k and j are in a modulo n range, even though you can write any k, j, and y that you want. It's automatically taking modulo of them. We know that any matrix function, either constructed or the shift operator, or constructed of matrices that commute with the shift operator, matrices that are same any place on an infinite line or on a circle, it will just be a scalar function, one-dimensional function on each subspace. So these eigenvectors are great. We take a matrix function, big complicated thing. We multiply them by an eigenvector. And what it returns is an ordinary scalar function of the eigenvalue corresponding to this, just a complex number. So our knowledge of the eigenvectors, matrices, eigenvalues enable us to reduce all computations which are translationally invariant, meaning they commute with the shift operator. Any function like energy of some configuration that doesn't depend on your choice of origin will be simplified by this calculation.